Exercise 2. Are the probabilities calculated in exercise 1 theoretical or empirical? In general, in science, or even in plain English, empirical means obtained through observation or experience. An empirical probability is that which we obtain as a result of an experiment or an observation. On the contrary, a theoretical probability is that which we obtain without experiment or observation, just by reasoning according to a number of premises. The probabilities obtained in exercise 1 are empirical because they are based in what we observed in that particular college. What we are going to practice in the following exercises is how to obtain some simple theoretical probabilities. Exercise 3. We roll 2 regular dice. Letter A. If we sum the 2 dice, what's the most likely result? What's its probability? To answer this question, the first thing that you need is the sample space, which is commonly defined as the set of all the basic and divisible outcomes. In this case, the sample space is this. We can see a 1 in the first die and a 1 in the second die, a 1 in the first die and a 2 in the second, a 1 in the first die and a 3 in the second, and so on. Also, we can see a 2 in the first die and a 1 in the second, etc., etc. So this sample space has 36 elements. What's the probability of each of these elements or outcomes? The premise that we accept is that all these outcomes are equally likely, which is based in the premise that in every die, each side of the die is equally likely to show up. If so, each of these 36 outcomes has a probability of 1 out of 36. Notice that 2-1 is different from 1-2, but 2-2 is the same as 2-2. I mention this because 2 common mistakes when getting a sample space are double counting individuals or not counting some of them, thinking that they are the same as others that were already counted. We call these elements ordered pairs because the order matters. Now we can answer question A. For this outcome, the sum is 2. For these outcomes, the sum is 3. For these outcomes, the sum is 4. For these, 5. For these, 6. For these, 7. For these, 8. Here 9, 10, 11, and 12. So which sum is the most likely? Clearly 7. Any other sum contains fewer outcomes. What's its probability? 6 out of 36, which equals 1 out of 6, which equals approximately 0.167. The formula that we have been using all the time is what we call the classical definition of probability. Probability of A equals number of cases or outcomes in A divided by the total number of cases or outcomes. As a consequence of this definition, a probability is always a number between 0 and 1. Also, the probability of the complement of A, that's to say the negation of A, equals 1 minus the probability of A. These properties are true even if we use other more modern or more sophisticated definitions of probability. Let's answer question B. What's the probability of the event the sum is 8? As you can see here, there are 5 outcomes for which the sum is 8. So the probability is 5 out of 36, which is approximately 0.139. Letter C. What's the probability that the sum is 6 or at least one of the numbers is a 2? This is what we called a combined probability. We saw how to solve this in the previous part of this class. For the sum is 6, these are the outcomes. There are 5 of them, so the probability of this part is 5 out of 36. For at least one of the numbers is a 2, these are the outcomes. Count them and you will see that there are 11. A common mistake here is saying that there are 12. Some people make that mistake because they double count the 2. Don't do that. So the probability of this second part of the event is 11 out of 36. And now, according to the formula that we saw in the first part of this class, we must discount the joint probability. In other words, the elements that were double counted even if we did not double count the 2, What are the elements that have at least a 2 and for which the sum is 6? The 4, 2 and the 2, 4. So we subtract 2 out of 36. And the final answer is 14 out of 36, or approximately 0.389. What's the probability that exactly one of the numbers is a 6 and both of them are even? This is what we called a joint probability. For exactly one of the numbers is a 6, these are the outcomes. We don't include the 6, 6 because it does not have exactly one 6. But on top of this condition, we still have a second one. Both numbers must be even. So we can keep only these two outcomes and these other two outcomes. Therefore, the final answer is 4 out of 36, or approximately 0.111. Exercise 4. From a regular deck of cards, we randomly select a card. The sample space here is simply the deck of cards. Remember that the deck has 52 cards divided in 4 suits, so there are 13 cards in each suit. The premise here is that every card is equally likely to be selected. Letter A. What's the probability that the card is of hearts? This couldn't be any simpler. 13 hearts in a total of 52 cards, 1/4 or 0.25. Letter B. What's the probability that the card is a 5 or of clubs? This is what we call a combined probability, so we must use the formula. The probability of selecting a 5 is 4 out of 52 because there are 4 5s in the deck, the 5 of spades, clubs, hearts and diamonds. The probability of selecting a club is 13 out of 52. The probability of 5 and clubs is 1 out of 52. There is 1 5 of clubs in the deck. This was double counted and we are now discounting it. So the final answer is 16 out of 52 or 0.308. At this point, I want to repeat that all these probabilities that we are calculating now are theoretical. They are not based in observations, but in certain premises. Let's go with the last exercise about theoretical probability. Exercise 5. In this roulette, the probability of winning is 0.2. Laura spins the roulette and then John spins the roulette. Letter A. What's the probability that both win? This is a joint probability. This is the probability of Laura wins and John wins. Here we need to accept the premise that Laura's spin and John's spin are independent, which makes perfect sense to me. If for some reason the spins were not independent, we wouldn't have enough information to answer this question. We would need to know the conditional probability. We saw in the first part of this lesson that if the events are independent, the joint probability is the product of the marginal probabilities. The probability of Laura winning is 0.2 and the probability of John winning is 0.2, so the final answer is 0.04. Letter B. What's the probability that John wins and Laura loses? This is another joint probability. Again, assuming independence, this must equal the probability of Laura losing times the probability of John winning. This is 0.8 times 0.2, so the final answer is 0.16. Calculations like these are going to be important in the next chapter when working with what we call the binomial distribution. Be sure to understand this exercise 5. In exercise 6, we mix empirical probability and theoretical probability. Let's talk about the game Stay or Switch. In this game, you must find the ace of spades. I have 3 cards. 2 of them are a joker and 1 is the ace of spades. I shuffle them and you pick 1 card. Let's say that you pick this. Now I show you one of the jokers. I show you that the ace is not here. And now you have 2 options. You can stay in your card or you can switch to the other. What would you do? Obviously, you want to do what has the greatest probability of success. So the question here is about two conditional probabilities: the probability of success given stay and the probability of success given switch. How can we calculate these two probabilities? The first thing that I do is playing this game 30 or 40 times in class with my students. In this way, I can get an empirical probability. If a student stays, I write here the outcome. If the student switches, I write the outcome here. You can play this on your own with a friend, and there are also apps online that allow you to play it alone. When I play this game with my students, the specific numbers change from time to time, but the qualitative aspects of the outcomes are always the same. This is an example of what I usually get. First thing that I observe, students are clearly more inclined to stay than to switch. I guess this has something to do with human nature. Once we make a decision or a choice, we somehow establish an emotional bond, and it's harder for us to switch than to stay. I must say that this possible explanation falls out of the scope of statistics. Statistics doesn't tell us the why, it just helps us see what happens. This being said, we can easily get the empirical probability of success given stay. 26 students chose to stay. Among them, only 7 succeeded. So the empirical probability is 7 out of 26, approximately 0.269. We can also get the empirical probability of success given switch. 14 students chose to switch. Among them, only 8 succeeded. So the empirical probability is 8 out of 14, approximately 0.571. As you can see, empirically, the conditional probability of success given switch is much higher than the conditional probability of success given stay. We can quantify how much. If we divide the big probability by the small, we get 2.12. So we can say that in this sample, the empirical probability of success given switch is 2.12 times as big as the empirical probability of success given stay. The next challenge is getting the theoretical probabilities. What's the theoretical probability of success given stay? I usually hear two answers, 1/2 and 1/3. Most people answer 1/3, which is the correct answer. The reason is that if you don't switch, you will succeed if and only if you chose the A's when you made your original selection. And when you made your original selection, you clearly had 1/3 chance of picking the A's. So if you stay, your probability of success is the same as you began with, 1/3. The reasons why some people answer 1/2 are interesting though. They could lead to a nice discussion about some classic controversies or fallacies in probability. Let's focus now on the theoretical probability of success given switch. This is harder to figure out. The answers that I commonly hear are 1/2, 1/3, and 2/3. The most common answer, I think, is 1/2. The right answer is 2/3. What happens is that a person that switches will succeed if and only if they chose the joker when they made their original selection. And the original probability of selecting a joker was clearly 2/3. Therefore, this 2/3 becomes the probability of success if you switch. Notice that in both cases the empirical probability underestimated or underrepresented the theoretical probability. The proportions are, however, much closer. In theory, the probability of success given switch is exactly twice as big as the probability of success given stay, pretty much the same as we got through our experience. Notice also that the empirical probabilities got closer and closer to the theoretical ones as we increased our sample size. When we had only 3 students who had stayed, the empirical probability of success given stay was 0. And when we had only 3 students who had switched, the empirical probability of success given switch was 1. When we had double sample size, we saw our first failure switching and our first success staying. As we kept repeating the experience, the numbers began taking shape. This is part of what we call the law of the large numbers. What this law says is that the larger the sample size, the larger the number of repetitions, the more clearly the mathematical principles and patterns will emerge, and the more closely the observations will adhere to those mathematical principles and patterns. This law is crucial for the business of casinos or houses of games. They design their rules so the probabilities favor the house. They may get unlucky and lose money one night, or 2 or 3 days in a row, but it's virtually guaranteed that their gains will give them profits at the end of the week or of the month. Professional poker players are also aware of this law. They usually say that poker can be frustrating because you can play perfect and still lose. But if they keep playing great, eventually they will get even and win. That's how they can do that for a living, thanks to those who don't play so well or don't do it consistently. In class, I play this game 30 or 40 times. The last question is, what will the empirical probabilities be if we play the game 3,000 or 4,000 times? I can tell you with such a massive amount of repetitions and according to the law of the large numbers, the empirical probability of success given a stay will be almost exactly 1/3, and the empirical probability of success given switch will be almost exactly 2/3.